Okay, though we have sparse attendance now, I'll start with the one and only interesting doubt sheet question. So, this question is coming from the proof that we did of convergence of PGD about limit of an average versus limit of the sequence. You remember that discussion? So, here is the question. There are two statements over here. Okay. If the limit of an average converges to some number, does it imply this statement? That is the question. Right. In our proof that we did, we basically looked at this something like this: function average of the function values was converging to something. But the more interesting thing was, does f of xn itself converge to something? That is what we wanted to know. So, do you think this follows, and do you think this follows? Two implies one is what you are saying. What about one implying two? Huh? No, because yeah, but okay, so let's take your argument. She's saying that at large values of n, uh, each one of those has a small weightage, so divide by n, it goes away. But if they have converged to a certain value, then I have a large number of them getting divided by a large number, right? X 1000, X 1001, all of these guys also the same value. So I have a large number summing up, and I'm dividing by a large number. So that, okay, why? Right, so exactly. So to prove something is harder, to disprove all I need is a counter example, right? So if I take wait, let's look at that. Supposing this is the sequence, right? So it's minus 1, 1, minus 1, 1. What is the limit of the average? Why is it 0? I mean, supposing I have a odd number of terms, then the sum is 1 by n tends to 0. That's why this converges to 0, right? But the sequence itself does not converge, right? So this is a counter example which shows that 1 does not imply 2, but 2 does imply 1. If I have 2, how will I show this? Hmm? Hmm. That is the intuitive way. What we could do is simply this summation of xi by n. Basically, this is the term that I have to see, right? What is the limit of this? Is this equal to 0? That's what we are asking, right? So if I subtract, I can just write this as summation xi minus n times x bar by n. I is equal to 1 to n, right? And I could just rewrite this differently as x1 minus x bar plus x2 minus x bar, right? Xn minus x bar. Now, if n is very, very large, what can I say about each of these terms? So we are saying that you're given that xn, you're given this, right? So for larger terms, what will happen over here? This is almost epsilon, you can say. What about these terms? They need not be 0, so they are finite, right? But finite divided by large n, 0. So this is actually equal to 0. So right, so 2 implies 1, 1 does not imply 2. Okay, so this was one doubt sheet question. Any questions on this? Quite intuitive, right? So the proof that we had for convergence was a weaker kind of a proof, but as I said, there are stronger proofs that can be used. Okay, so now let's proceed with projection operations. Okay, so what example did we take so far? We took the projection on the L2 ball, right? How did I write that? So the projection operation was this: find the x that belongs to omega, which is closest to argmin would be x naught, would be x. Okay, so we've already done this when L2 ball. We did this, okay, and that's fine. This is the easy part. Let's say that there is some problem where instead of this 2 norm, it becomes the 1 norm. Okay, so supposing, let us say sigma is such that x okay. Now this, it on one end of it, you can interpret this as just some mathematical exercise. So instead of 2 norm, I took 1 norm, right? But there can be several applications or scenarios where this is a very realistic problem. For example, you have a city block kind of a thing. Your pizza source is over here, delivery is somewhere over here, and the pizza guy obviously cannot just go like this, right? The pizza guy has to go like this, in this kind of a way, right? So what is the cost incurred is going to be proportional to how much the delivery person has to walk, and how much the delivery person has to walk is going to get captured by the 1 norm of x, not the 2 norm of x, because that's the crow flies according to the 2 norm. The delivery guy has to follow the blocks, right? So I may have a constraint that if assuming the delivery guy has, let us say, a motorcycle or walks at a certain speed, and I want to ensure delivery within like Domino's, right? 30 minutes has to be done. So I may want to put a constraint that 1 norm of x has to be less than equal to 30 minutes in whatever units you choose, right? And solve this problem for me. The problem could be minimize the cost, minimize how cold the pizza gets, whatever, right? So these kind of constraints are fairly regular, okay, and they appear. On the face of it, is there any problem with this constraint? Like, how would I define this constraint in my usual language? So c of x, what will I write c of x as in the normal notation that we have been following in this course? So it's is it equality or inequality? Inequality. Inequality constraints are written as c of x greater than or equal to 0, right? So what is c of x, right? So it's 1 minus norm of x greater than or equal to 0. Okay, now this looks like a fine enough constraint. All that I have to do is to solve. What would I do in constraint optimization? I have to, the first step would be to form what? I have a constraint, I have some objective function, I'm giving you the objective functions f. Feasible set is given to me from c of x, that's formed. What's the next step? Form the Lagrangian. So I would write Lagrangian is this. Okay, let us say all the if conditions of the KKT theorem hold true. Very good, I go to the next step. What is the first statement of the then part? grad Lagrangian, right? Supposing I'm being nice to you, I tell you that grad f, I tell you f is differentiable, so no problem. What about c? Grad c, do I have a problem? It's not differentiable at whenever any of the components. So what is x, one norm of x, right? Now mod x, if you just take the scalar function mod x, which looks like this, it is differentiable everywhere except 0. So I have a problem in taking gradients over here. So what do I do? Right, so here is where we have to upgrade our definition of gradients, okay, because we will come across so many problems where I need to differentiate a function that is not differentiable, okay. So let's go to the next page. So subgradients is right. So we are going to learn a new concept of a derivative which generalizes the idea of a derivative. So it's a pretty fundamental concept, okay. So I'll start, we'll restrict ourselves to convex functions, okay. So let's start with something very basic. So for take a very simple case, if I give you a differentiable, okay, convex function, okay, one for which I can draw a very convenient graph like this. Let us say this is my f of x, okay, I am at some point over here and this is my x axis, okay. At this point x, let us say this is what the gradient looks like. So, and let us say now I am at some point y over here, okay. So there are a few important points over here. There are these 3 points marked in the black circle, okay. So if I form the linear approximation of f, okay, at x, we did that in the last class, what would it be? So this is the first order Taylor approximation of f at x. What all would I write in it? First term would be f of x, that's the first term of Taylor's theorem. What is the second term? Grad f at what point? X, next transpose, next y minus x. This is the first order Taylor theorem for this function, and I've taken the starting point as x over here, okay. Now given that this is a differentiable function, means grad f is defined. I'm in my usual world where gradients are defined, no problem. If it is a convex function, what is the relation between these two quantities? Greater than equal to, right? Okay. So we already know this, we did this in the last class. This is almost like the definition of, many people will write this actually as a definition of convexity, okay. Now we are going to give this another interpretation. Let's focus on the right hand side, okay. Now this has been drawn on a 2D piece of screen, so it looks like a line. Now imagine x and y, they are all living in n dimensions, okay. So in n dimensions, this object on the right hand side, right, it is a function, x is fixed, y is the guy that is varying. What kind of a function is this? Is it what is it, exponential, trigonometric, what is it? I want something more precise than linear. If you're, it's an affine function because there is an intercept which need not go through the origin. That's the difference between linear and affine. Linear always goes through the origin. Affine need not, can have an offset. So this is an affine function. Another word for an affine function like this is a people will call this a hyperplane, right? Why hyper? Because the dimensions may be more than 3. So instead of just calling it a plane, which we are used to in 3D Euclidean space, you call this a hyperplane. Okay. So this, because of the way it kind of supports the function f, this is also called a supporting hyperplane. Okay. So you can almost think of a gradient for a convex function as something that supports the function that is opening up above it. Okay, so hence the words supporting hyperplane. And this gives us a very convenient way to try to come up with a little bit more general definition of the gradient. Okay, so let's see what that means. So now I'm going to define a subgradient. And I'm going to stay on convex function. Okay. So I've kind of just replaced, doesn't look like I've done much. I've just removed this grad f and put g inside it, right? So what is it saying? A subgradient g of a convex function is such that this property of supporting hyperplane is still maintained. And we know that for a convex function which is differentiable, if this g, if I replace by grad f, this grad f will always support the function like a supporting hyperplane everywhere. Where does it get interesting is if the function is not differentiable. So let's have a look at that. Okay. So imagine a function that looks like this. So it's like this. This is looks like a convex function. However, it has a kink. Right. So this is my function x. Right. So at this point over here, do you think, does it look differentiable at this point? No, right? Because derivative from the left, derivative from the right, they are not matching up, right? So if I draw the tangents over here, if I am coming from the left, this is the tangent, right? If I am coming from the right, so this is like a textbook example of a function that is not differentiable. Okay. Now that said, each of these guys is like an affine function, these tangents which I have drawn, right? So if they are affine functions, what is different between these two affine functions? So at this point x, I can write all sorts of different affine functions that pass through x. What will their form be? So this thing on the right hand side, you all agree is a affine function or a supporting hyperplane. Now I tell you that at this point x, I want to write a general form of a affine function which passes through x and has some random slope. How would I write that expression? What would change in this expression? Union, no, we are, give me just one way of describing it. Before you come to union, give me one single guy. What, okay, let me make it even simpler. In this expression, what should I change so that I can go from the blue slope to the blue line to the pink line? G is the only thing I need to change, right? So in fact, I can write this guy as f of x plus g1 transpose y minus x. That's the blue line, and the pink line I can write as f of x plus g2 transpose y minus x, right? And both of these guys have the property. Can you say that both of these lines, are they supporting hyperplanes for this function at x? Yes, right. So they are both okay. There's another way of identifying a supporting hyperplane. The plane never cuts the function. You can see that this, neither the blue line nor the red line ever cuts the function, right? So you can say alternatively, uh, So in technical language, you will say that G1 and G2 are the subgradients of f at x. That's how we would call them. G1, G2 are so this is of course something new. We are used to, if you give me a function f of x, I calculate the, if I am in class 11, I would do df by dx. Now after that I do grad f. We are used to, it's very hardwired on us into thinking that grad f is a unique function. But now we have generalized the idea of a gradient to a subgradient, and I am telling you that both G1 and G2 are subgradients of f at x, right. So that's how this idea is generalizing, that we are replacing something that is unique by something that is non-unique, however, which seems to satisfy the same or have the same properties as the gradient did. In particular, the property was that of being a supporting hyperplane. That's how I'm generalizing it in this way. So let's see what that buys us. But is this clear? Properties of supporting hyperplane. There is no argument that both G1 and G2 seem to be supporting it, right? Okay, let's go to the next page. So as I just said, since there are so many different possibilities of G1, G2, in fact, let's just go back there. Do you think G1, G2 are unique, or can there be some other supporting hyperplane as well? There can be, right? I can, for example, if I take a line like this, if, in other words, if the slope is between G1 and G2, it is also a supporting hyperplane, right? So it is also a subgradient, right? So it's definitely not unique. It's not that it has two values, it has an infinity of values, right? So when I have a whole bunch of things which are possible, you remember we had this situation happen when we were defining feasible sequences. Feasible sequences gave us tangents, and then when I collected all of those tangents, and what did I call it? Tangent cone. So same concept is happening over here. I have a lot of subgradients. I collect it all together, and what do I call? I call it a subdifferential. Okay, so that's the next concept. The symbol for it is this. This is the symbol. Instead of grad f, now I have this small del f. Okay, and this is defined as G. And the same definition that I had for the subgradient is just over here. So any G which satisfies the supporting hyperplane property is works. Okay, so this is the subdifferential. Okay, it happens to be a closed convex. Right, so let's take an example to further. Yeah, question. Yeah, it's defined at a point x. Okay, so let me just write it like this. Oh, the previous. You mean this line over here? This is in general true if you take any, I mean this is just the property of convexity, that's all, right. So you pick any point x and pick any point y, this will always hold true. So this is the G correspondingly at that point x, at that point x. So let's take some simple example to get familiar with this concept. It does not depend on y, you can take y to be, so yeah, you can, the definition of convexity that no matter where you go, the function is always above the, that does not depend on how far you go, right? It does not depend on that. Okay. So I'm going to take an example where, draw this properly. This is, let us say, f1x, okay, and I have a second function that looks like this. I'm going to call this f2x, okay, and I'm going to define my function f in a slightly irritating way. I'm going to say right. So, if this is my function definition, how is it going to look? If I start from the left, I am going along the blue line, I go like this, and then I hit this point, what happens? I jump up, right. So, this becomes my f of x, okay. So, even though f1 and f2 are nice and smooth and differentiable, etc., the resulting f, wherever you have a max or a min operation, these kind of things can happen. There is clearly a point where there is a kink, right. So, now you have the situation where you can have this is the gradient at this is right. So, this is f1 dash at x, and then I can also have this is my f dash 2 at x, right. So far we have not yet come to subgradient. So now let's look at the cases when I need to, so you should also know when do I need to worry about gradients and subgradients, right. Like in the case of mod x, or sorry norm, one norm of x, or the function f of x equal to mod x, I needed to worry about differentiability only at the origin, right. So if I am far away from the origin, there is no problem, derivative is well defined, right. So the three cases that I will need to worry about is whether I am on the left of the kink, the right of the kink, or at the kink, right. Those are the three situations, right. So if f1x is greater than f2x, then what is my f? f1x, right. And what is the subgradient then? There is no controversy here, the subgradient. So if the function is differentiable, the subgradient becomes the gradient, right. So it becomes basically grad f1x without any controversy. The second situation, well, let's take the reverse situation, f1x is less than f2x. So f of x simply becomes f2 of x, and the subdifferential is simply grad of f2. Okay. Now let's take the case where f of x, f1x is equal to f2x. Alright. Now at this point we have the issue that the function is not differentiable, okay. But now we know that we have to take the idea of the supporting hyperplane. So I have f1 dash at this point, I have f2 dash at this point, and of course any of these guys will also work, right. So look back at the definition of the subdifferentiable, right. So it's all those g's which satisfy the supporting hyperplane condition, right. So in this case subdifferential becomes what? Correct. So I can any convex combination of grad f1 and grad f2, right. Another way of writing it is it's simply the interval, which one looks bigger, okay, never mind. It's any number between this and this. In this case, I am saying it's a number because I am drawing a slope on paper. So the slope is just going to be a scalar number, right. If it were, but you can see this generalizes to a vector also, right. So it's any number between this and this is permissible because it corresponds to a slope of a line with this red double arrowed structure. Any line with a slope between grad f1 and grad f2 is captured by this. That's the meaning of this, right. So just to put it into simple words, any number in this range, this is how you would just say it in English. Of course, what I am making the very simple assumption that numerically grad f1 is less than grad f2, right. So the set 1 to 2 makes sense, set 2 to 1 doesn't make sense, I mean the closed interval, right. So the beauty of it is that in numerical applications, because the subdifferential has a full range, it's actually, you can choose the range according to what you want. It's not, it's open, it's up for you to do it, okay. So is this fine? So let's go to that example which we were sort of motivating our study by, which was mod x, right? F of x is equal to mod x, okay, and we all know how that looks, right? So x greater than 0, what is grad f, I mean del f? 1. X less than 0, what is del f? Minus 1. X equal to 0, what is del f? Minus 1 to 1. Any number in this, right? So this is what I do, right? And this function should look somewhat familiar to you from Hinton's signals and systems. If I plot it, what does it look like? Right? It looks a little bit like the signum function of x. However, there is, well, okay, the signum function, how is it defined? Minus 1, 1, and add 0, what happens? You define it to be 0, right? Something like this. So is the signum function a subdifferential? Yes, because I can pick any value, 0 is any value, right? But there can be, if it's up to me, I could have chosen del f equal to minus 0.1765. So it's not the signum function, but it's a subdifferential. So this is a, you can say this is a good candidate for candidate.